Good afternoon, ladies, no gentlemen. I think I don't know, when does the session start? 1/2 or? A 4:15. Okay, then let's get it going. Yes. Yeah, yes, I will compensate it by speaking a bit faster. Anyway, yes, good afternoon, gentlemen. Very much welcome to the training session here. The last training session, I guess you are already a bit exhausted. I'm trying to make it as much as exciting and getting you excited about the coupling of the extended discrete element method to OpenFOAM. That's basically what is usually called an DEM CFT coupling. So we're basically coupling a discrete phase with a continuous phase. Continuous phase is OpenFOAM. The discrete phase are particles. In general, yes, a good example is always biomass combustion. So pellets, wood pellets or biomass pellets burning in a gas phase. And we have then, of course, coupling with different things between the continuous phase and the discrete phase. Yeah, so maybe I've structured my talk into a brief introduction, then some. I don't see, but anyway, some XDEM basics. Then the of course, the core of the talk, the Cftdm DM coupling with a tutorial case, implementation, and a summary. So essentially, you're going back to the introduction. Yes, I mean the thing. One reason why I'm doing that is because a particulate phase or particles are everywhere around us in the environment. So mining, then basically, yes, garbage, biomass, I mentioned already, blood cells, pharmaceutical industry. So basically, wherever you look at, you will see particles if you open your eyes. And then, yes, according to Mr. Richard, granular material are ubiquitous in nature and are the second most manipulated material in industry. The first one is water. So that gives you basically proof that particles are almost everywhere. So yes, that is already about the introduction, why we're doing that. And if you look around, you see reacting particles, combustion, what I want to say, yes, material treatment, whatever, in a lot of applications. Then basically the coupling. I'm talking, I mean, you're probably familiar with the DEM method. This is the discrete element method that basically describes the motion of granular materia in space and time. But as I say, updating velocities and the position, it basically describes the motion of material in space. And the extended discrete element method is derived from the discrete element method. And as I already mentioned, is based on the classical discrete element method and is extended by the thermodynamics for particles. And that means basically we're describing, yes, in the simplest case, the temperature distribution inside a particle. And if we're going to more elaborated cases, we're talking as well about the description of any kind of reaction progress or reaction that takes place inside the particle. And of course, there's coupled with temperature anyway. So basically, and of course, once we're talking about temperature and reaction or whatever, my simplest one is, for example, drying in a particle, we have, of course, the outer hull of the particle or outer boundary, and we have to find some transfer conditions. And of course, these transfer conditions, they have to come somewhere from. And that is basically where comes CFD OpenFOAM into the game, because we're going to predict the continuous phase, the temperature in the continuous phase, for example, in the gas phase, the temperature distribution together with the gas composition with OpenFOAM. And that means basically we need to have an interface to computational fluid dynamics, of course, here OpenFOAM. Or if we want to extend it, I will touch that only briefly later. If we want to have as well structure of fluid structure interaction or particle structure interaction, we need to as well have coupling to the finite element analysis, where we can take as well any kind of finite element code we're using, usually calculix. And yes, that's what I mentioned here. We have coupling to OpenFOAM and calculix, of course, obvious OpenFOAM for the CFD and calculix for the finite element analysis. Yes, basically, when we're talking about granular material, of course, we're having there, yes, a lot of granular material. Basically, there's one classification depending on the particle size range from ultra-fine powder, superfine powder, granular solid, and broken solid. And that's basically what we usually address as granular material. And the nice thing about physics is that basically physics doesn't care about the material size, because the physics, whether you have heating up of a particle, works in the same way for ultrafine powder as well for large particles, like particles up to a size of 1, 2, or 3 centimeters. So basically, this method is uniquely applicable to a large range of powder, large range of granular material, ranging from ultra fine sized powder to basically granular solid stones or whatever have this kind of size. And basically the DEM workflow is quite simple. If you look at the two particles, they come into contact, they generate a force, an impact force. That's basically what I wrote here as estimated impact force. Then sum up the forces sum up all the not all the particles, sum up all the forces for particles. So if there comes a gravity force, then you have the force acting on a particle, and then it's basically simply Newton's second law to get then the velocity and the position. Basically, you get the acceleration of the particle by dividing the sum of the forces by the mass. Then you have acceleration. You do first integration, you get the velocity. Second integration, you have the position of the particle in space. And that's simply the DEM method for motion. And of course, you do the same thing for the rotational motion. If you have other particles with another shape than spherical shape, you basically have as well the momentum. You do is first integration, you get the rotational velocity, and the second integration, you have the orientation in space. And that is, simply speaking, it's what's behind DEM to estimate motion and rotation of particles in space and time. Yes, and basically that's what I've just shown here quickly. So you have here two particles, you have here a contact plane, you have here the contact point, and you generate a force. A simple force model could be just a spring model. That means you have an overlap of the particles, you multiply that with a spring constant. A spring constant times a delta overlap gives a force, and then you have already the force that is acting between these particles, and that's basically the force driving the motion. And with the moment generated by this force, you have a moment acting on both particles, and do integration, and you have in the end what you need. So basically, the loop for such a particle or for such a DEM method simply is basically particle initialization. You do collision detection. That's mostly, or that's usually the most or the time consuming exercise in such an operation, to find contact partners and then to evaluate the force, the contact force, apply Newton's second law, you have velocity distribution, and then have your output data. So that is, simply speaking, the workflow, the algorithm for DEM. Yes, and no, that doesn't now work on this computer here. Oh, sorry. I'm sorry, the animation doesn't work. Don't know what happened. Sorry, but anyway. So and then basically that is just now what I've been talking about, the pure dynamics of particles. However, when we come to the thermodynamics of particles, we have to we have a wide range of processes that we want to cover or want to basically include into an extended discrete element method. I mean, obviously, the first things that we're thinking of is heating and cooling. So that means basically we're considering temperature distribution inside the particles. And there we have here convective heat transfer with a fluid, obviously, a fluid around a particle with a temperature difference between the surface temperature of the particle and the fluid temperature generates the heat transfer multiplied by a heat transfer coefficient, and the surface is the heat transferred. Then we have a second transport mechanism that's conductive heat transfer. That means basically particles that are in contact, which are their physical contacts, and they have a different temperature, they will change as well heat. And that is pure conduction. So basically on the temperature gradient and the contact surface times the heat conductivity gives you then an additional heat flux between the particles. And to complete the sequence, in addition, for higher temperature, we have radiative heat transfer between the particles. So that means basically heat transfer where the particles don't have to be in physical contact. So basically, if they see each other with a significant large Q factor, they exchange then a heat by radiation, and then it's taken as well into account. Obviously, should only be taken into account only for higher temperatures. Then, of course, when we're leaving the region or the realm of heat transfer, we're getting to basically mass transfer, and that involves then basically homogeneous, heterogeneous reactions, covering then the spectra between the shrinking and directing core model, meaning basically either we have only reaction on the surface of the particle, or we have a reaction progress through the whole particle, so basically that we don't see large gradients from the interior, from the center of the particle to the boundary of the particle. That is basically what is attributed with the shrinking and erecting core model. That basically, yes, means then reaction. And in addition, for a lot of processes in the columnar media, we have to consider phase change. And they're all familiar why one of them is drying, so meaning evaporation. If you have a wet particle, biomass particle, usually wood, they come with a considerable amount of moisture, 20% or even more, 40, 50%. And then you have to apply first the drying, or the drying is going to happen anyway. And this is basically called, it's then basically a phase change from liquid to gas. Then melting is just the other way around, from solid to liquid. And that you have basically ice melting, of course, liquid metal. Basically, if you're looking at the blast furnace, where we're creating liquid metal through melting of the iron ore particles, or another application is additive manufacturing, where we have this this fine powder, laser scanning over powder bed, applying a lot of heat to the particles, and of course they undergo the melting. And then the other way around, solidification, is coating of particles. That means you spray liquids on a particle, and they cover the particle, these liquids, and they, with the appropriate cooling rate, you will have the liquid that was sprayed onto the particle to solidify, and this way growing the particles. So that means always these, apart from evaporation, these melting and solidification come together with a size change of the particle, meaning the particle is shrinking or the particle is swelling, becoming bigger due to additional mass that is coated onto the particle. And then usually these, yes, sometimes phase change as well, but often these homogeneous, heterogeneous reactions go along with a change in the morphology of the particle. That means essentially the porosity inside the particle is going to change. And that, of course, has, if the porosity inside the particle changes, that is connected to the inner surface, and of course has a strong impact on the reaction rate for a heterogeneous reaction. Then basically, as conduction, I've already mentioned. And then, yes, last but not least, for all these, are basically these reactions taking place inside a particle, that is accompanied with a diffusive transport in the particle. That means we need to evaluate the diffusive transport of all the species that may take place in the reaction system, or may be present inside the particle. And that is basically, yes, based on Lennard-Jones potentials, meaning you basically evaluate first the diffusion of each species inside the other species, and then from the binary diffusion coefficients, you evaluate then the total diffusion coefficient for species in the mixture of the species mixture. Yes, essentially what we then doing for the particle after all these things, or these things are described by, yes, conservation equation of mass, momentum, and species. You see here, and we basically say, okay, the particle or the particle geometry allows a one-dimensional discretization. So basically in the radial direction, for which we then solve in this conservation equation for mass, momentum, species, and last but not least as well for the solid and liquid spaces, where we assume that the solid spaces anyway, but liquid spaces as well, that are not moving inside the particles, so they basically undergo any kind of reaction. And then of course conservation of energy in the same way, where we're taking into account the conduction here, and then of course on the right hand side reaction term due to phase changes, whatever we may apply. And boundary conditions, for the heat, basically the gradient at the particle surface is equal to the heat transfer. That's very here, the convective heat transfer with a heat transfer coefficient, radiative heat transfer and conductive heat transfer. And the same, of course, applies to the mass transfer coefficient times and concentration difference gives you the gradient of the diffusive gradient. And you basically see here, a simple representation. Here the particle, here a CFD cell, the particle is in, and the CFD cell, basically OpenFOAM or CFD, is going to give us the fluid temperature and the concentration or the gas composition in this cell. And that are basically the boundary condition for the particle. So we'll be evaluating this right-hand side here with the TR, that's the temperature at the surface of the particle, minus T infinity, which is then here the fluid temperature. And that essentially completes the whole coupling procedure in XDEM. Of course, the particles, they always see the same physics. What they see are different boundary conditions depending where the particle in the CFD space is. You see it sees different temperature, different gas composition, and therefore as well then each particle has a different history in terms of heating up, reaction progress, and so on. Yes, and if you look in such a particle, you see here the temperature. This is the temperature evolution via radius and time. So basically here a simple heating up process of a particle. Don't have to go. And basically there is just a brief summary on the basics of XDEM in terms of thermodynamics. And now I'm going to basically introduce you to the Cftdm coupling. And that means basically, the coupling was already mentioned. For what we have to consider are the three basic entities, that's heat, mass, and momentum. And if you look at the equations here, they are very similar. Of course, you have always a transfer coefficient alpha, the heat transfer coefficient, beta, the mass transfer coefficient, and CD, the drag coefficient, times the particle surface, times a relevant difference of either temperature, concentration, or velocity. And that gives you basically the interaction between the fluid and the particle. And these terms are obviously appearing for the particle as a source term due to the boundary conditions, a positive, and of course on the other side in the CFD as a negative source term to conserve both always energy, mass, and momentum. That means basically heat that is transferred onto the particle for heating it up is the same heat that cools down the fluid in the CFD environment. Yes, and that basically means the simplest way to basically transfer these properties between the CFD and the DEM is basically you go into the what I wanted to say, the relevant equation, for example, here the energy equation, and you just add on the right-hand side a heat source. And that's it. And the same, of course, this heat source, you populate this heat source vector with all the looping over all your particles and evaluating the appropriate heat transfer with the CFD cell temperature, for example, and you're putting that on the right-hand side for the CFD code in the appropriate column, what corresponds then to the cell number, and you have it straight away, and then OpenFOAM is solving it. The same obviously for the mass for the pressure equation in OpenFOAM, simply equals mass source. That means basically if you consider mass transfer between CFD and DMM, beta times the concentration difference, positive for the particle, negative for OpenFOAM as a source term. And the other one is, of course, for species. Okay, you have usually a number of species to consider. So basically, you take if you look over all the species, you take your mass source I, that is then the species oxygen or whatever, and you put here the mass source on the right-hand side, and the whole thing is done again. A more, let's say, elegant method without manipulating the source code. So you just you don't have to manipulate the solver, is to use the FV options or the FV model. And that's basically you define here in the constant directory, what I wanted to say, the FV option or FV model in the latest version of OpenFOAM, where you basically just define a type, what type it is. And you basically have to say that's basically, that is the file where the OpenFOAM finds all the information. And here it tells, you tell OpenFOAM where it has to go. For example, here, if this is a multi-phase application with liquid 1, you say, okay, the total particle mass source, that's basically if the particle is melting. We have then liquid that is transferred into the OpenFOAM phase of liquid 1. This is the file where we have all the information available, and it goes into thermo_flow.liquid1. Yes, the same is for the species source. Again, the source O2.gas to tell OpenFOAM which phase it goes to. And then, of course, the injection rate as U is then O2.gas, nothing. And the same for the energy, again here, source.gas, and it goes to E.gas. So that is basically, simply speaking, the way to make OpenFOAM aware that there are additional source terms that have to be considered coming from a granular phase. Now, basically, yes, an introduction to the tutorial case. I would have liked to do that interactively on my computer, but it was a bit too risky to couple here the whole system, the whole thing, my Ubuntu system into Windows, and they usually don't speak much very good to each other. So, but anyway, I have chosen a very simple case here. 9 particles in such a column here, obviously from the bottom here, inlet velocity with a temperature of 160 centigrades, and on the top the outlet, and the other way around is just walls. And essentially, yes, the particles have an initial temperature of 25 centigrades, diameter 3 centimeter, and initial moisture content of 20 degrees. And I've chosen a very simple example here for the sake of simplicity, but it basically includes all transfer mechanisms that we have been talking about. And you can expand these things easily by adding more reactions or more complex thermodynamic processes to a particle. So essentially what is going to happen is that, the hot air comes from here, enters the domain. Particle is 25 degrees, so we have a temperature difference delta T. That means we're having a heat transfer, and I included as well evaporation here as a simple process. That means at some stage when the particles have reached the evaporation temperature, then evaporation starts, and we generate vapor inside the particle. This vapor is transferred into the CFD phase, and we're going to see that later as a distribution of vapor in the CFD phase that, of course, is then transported with the velocity up to the outlet. Yes, so basically what you see here is the source term. That is basically the source term H, so vapor. And you see here essentially this is the region where we have the particles. And you see that we're having here a space dependent for each CFD cell. We have a different source term. that we see due to the particle process, to the coupling with the CFD in terms of temperature coupling, and of course as well in terms of, I wanted to say, mass transfer coupling. And it's always a, yes, nice, not for this simple case, but in general, to look at the source terms, how the distribution is, and in particular, how it changes. Yes, here now the, what I want to say, the particle as well included. So again, here the distribution in the CFD phase for the vapor, and as well the liquid mass inside the particles. So you see basically here, these particles, they have already less liquid than the upper layer here. That obviously the physics demand that. And of course, here the air comes with a temperature of 160 centigrades. We have heat transfer. That means the particles are heating up and the fluid temperature is cooling down. So these particles here, they see already at fluid temperatures certainly less than 160. And therefore, we have less heat transfer. And less heat transfer means, of course, less evaporation. Yeah, here the heat source, as I mentioned here in this layer, yes, the somehow dark blue indicates a strong negative heat source because the particle is heating up, so the fluid is cooling down. Therefore, negative sign for the heat source. And here in this layer, of course, a less strong heat source because we have less heat transfer for the second layer of the particles. Then surface temperature of the particle, gas temperature, basically reflecting what I just mentioned. You see basically here the bottom layer of particles have surface temperature of 419, whereas the particles here have something like 413 or 412. That comes due to the fact that the second layer, or the particles in the second layer, they see a fluid temperature is certainly less than 160 centigrades. Yes, then here again, the mass source coming from the mass transfer. Here the mass source, of course, basically here inside the fluid domain positive, because we're transferring vapor that has been generated inside the particles due to evaporation into the fluid phase. That means basically the gas phase, yes, the gas phase sees an incoming flux of vapor, meaning the particle source has to be positive. Yes, again here, density the same, reflecting here. The density is increasing, obviously, from here to here, because we're having here in this layer and this layer injecting mass into the system, and that obviously increases the density. And here, basically, yes, the advantage of such a coupling is, of course, that you can, or you're basically predicting the particle or the state of the particle, the thermodynamic state of the particle over the whole simulation time. That means you can trace basically the history of any particle in your system and see what is happening to the particle over the simulation time. And this is just here a snapshot from one particle that I've picked out of the system here. And you see basically that is showing here the temperature of the particle we are here via radius and time. And you see basically starting here, the particle initial conditions, something like I think 270 or 290 Kelvin, so constant particle temperature over the radius. And you see basically here, 1 means the particle surface, so where we have the boundary conditions, that due to the heat transfer or the temperature difference between the fluid and the particle surface temperature, we're having here a rather strong gradient, meaning the heat at the particle surface is rising rather quickly, what is obvious. And then, of course, with the conductivity of the particle, heat diffuses into the interior of the particle, of course, and at some stage at the center of the particle, we see as well a rise of the temperature, but of course only with a delay because heat needs to be conducted from the boundary, from the surface of the particle to the interior of the particle. And then basically, yes, as soon as we have reached here the evaporation temperature, that is what you see here, this plateau-like area here. then the temperature is not increasing anymore, because when we reach evaporation temperature, the incoming energy is consumed for evaporation of the liquid. That means temperature is not changing anymore. In the same way, when you're melting ice, the ice melting process is taking place at 0 centigrade. The same way here, evaporation takes place at evaporation temperature. And this is kind of plateau-like area that we have here. And only, of course, we will have, of course, the first dry region of the particle at the boundary or close to the boundary. That's what we see here. Then the particle temperature rises again. And the same, of course, and then we have basically a kind of drying front propagating through the particle from the boundary to the interior. And that's what you basically see here. This kind of yellow line is basically indicating, yes, a bit lower here, the rim of the plateau-like surface here, where then basically all vapor, or not all vapor, all water inside the particle is evaporated. And then, of course, the temperature can rise again to, yes, to basically a steady state value once for, yes, here this case for 2,500 seconds. Yes, and you see here basically a different representation. The water mass fraction, you see, I said we had an initial evaporation or moisture content of 20%, so 0.2. That means here again, you see that the over time here, the the moisture mass fraction is dropping to 0 according to this drying front that is propagating through the particle. And the same for the porosity, that what I mentioned already beforehand, that usually the water is inside, or if you take biomass, if you have dry biomass, you have a certain porosity of the wood, and water usually that is coming with the biomass is stored in these porosity structures, in a pore structure. That means basically when you remove water by evaporation, the pores open up because the water is removed. And that means basically that we're having here, yes, again, the porosity increases from 0.4 to 0.6. That makes exactly this 20% of moisture content that we had initially. And that's basically as you see again, a kind of wave front that is propagating through the particle and affecting the porosity distribution. And this is, of course, important for later if you take biomass, the combustion of biomass, that is then usually a heterogeneous reaction. Of course, the porosity distribution inside a particle is important for the diffusive process of oxygen into the particle and then the reaction process. Yes, and you see here basically an integral representation, the drying of a packed bed from total mass fraction 1 to 0.8, so 20% again what we removed. And that is basically here, yes, for all the particles. So that is basically quite a handy thing. If you have a packed bed of a moving bed, we have integral values of the whole packed bed in terms of, yes, for all the species that we have inside the total mass, the dry mass, and whatever you may think of. So basically you see then basically with this kind of data, the integral data, there is data that you then basically can compare to for performance issues in terms of, yes, in particular, if you do, for example, a lab scale experiment with drying of a packed bed, then you basically you cannot measure the weight loss of an individual particle. You basically specify the weight, measure the weight loss of the whole complete packed bed, and that is what you would measure this line, and then you can compare straight away to the experimental data. Yeah, I guess this is not working either. I will give it a try. No. But if you, okay, we'll explain that later. Yes, but this is basically when you have, I mean, this was basically the raceway that is in particles moving in a fluidized bed. So we have very strong motion of the particles. So they move very strong inside the temperature field of the fluid phase and the gas composition of the fluid phase. And that means basically depending where the particle moves and where it is, it sees a lot of different, in its lifetime, it sees a lot of different fluid temperature and experiencing different mass transfer ratios. And that's what you see basically here. I mean, we have here again, one is the surface of the particle, and you see here these fluctuating values for the temperature. And it's exactly due to the motion of the particle inside the CFD domain. And you see here basically, yes, fluctuation. And of course, these fluctuations are flattened out by the thermal inertia rho P of the particle, so that you basically, yes, a few layers into the particle, you don't see much of these fluctuations anymore. But on the boundary, on the surface temperature, these fluctuations are quite significant. And of course, these fluctuations in particular, when you look at the surface reactions, or surface reaction of particle, then these fluctuations have a strong impact on the reaction rate. And taking then a kind of average temperature is not going to be all right. It's the same here for the CO mass fraction. That was basically, yes, yeah, the CO mass fraction as well. Here, of course, the fluctuations are a bit higher than for the temperature. Of course, I think the ambient condition of CO mass fraction was 0. That means basically whenever we have a production of CO inside the particle due to the combustion, we have a transfer to the what I want to say, to the CFD phase, and of course then therefore as well, yes, a strong fluctuating species mass fraction on the particle surface, and that here reflects as well then the yes, strongly transient behavior of the particle when it was moving inside the CFD domain and going to see different temperatures. Yeah, then the implementation is rather simple. I mean, when we started the whole thing, the implementation was not that simple. But now with the experience we've gained, it's rather simple. You identify your appropriate OpenFOAM solver that you think is okay for your problem. Then you basically insert 3 sections into the OpenFOAM solver. You modify the options file with XDEM interface files. You compile the thing, link the coupled solver, and run the shell script. That is simply all you have to do. And yes, I wanted to show you, yes, the source code for the reacting foam solver. Essentially, these reacting foam solvers, you have the initialization phase, you have a time loop, and you have the termination phase. And that's exactly these 3 locations where you insert your lines. So you copy and paste the lines of XDEM. You don't have to take a picture. You will be after the summer break, it will be available on my homepage. You can download everything, and you can compile it and run it and play with it, whatever you like. So yes, so basically, as I said, you have the initialization phase. That's why we'll copy as well the XDEM statements to initialize XDEM and to make the coupling between the fields of OpenFOAM and XDEM so that the right data goes to the right CFD OpenFOAM fields. Then you have, of course, inside the time loop, you insert the integration for XDEM. And you have as well at the after the time loop statement XDEM terminate to basically release memory and things like that, and that's done. So it's simply like that. And then you basically have a source, a script that defines a few things. Maybe first there's of course source OpenFOAM 7. Then you define the executable, where the executables are, and the libs, and of course as well the material properties for XDEM. That is here basically data there we have stored basically all in H5 in the compressed H5 format, material properties for biomass, for I don't know what, and as well another subdirectory is the reactions, the chemical reactions, where all the reactions are defined. So that basically means if you want to, you are not limited to use what is available. You can create your own material, you can create your own reactions, and you can have their maximum flexibility to adapt the particle to any kind of process that you would like. So that's basically you take your particle, you define the material, and then you attach any kind of reaction, one reaction or reaction mechanism to it to define whatever you like. And then, of course, you basically execute the solver reacting foam coupled, and that it's basically, and then you get, yes, obviously the same from OpenFOAM, the same directory structure with the time output. And for what I wanted to say for XDEM, you get an H5 output, and you can basically open both. I think I don't have no. You can open both in ParaView, OpenFOAM as usually, by opening a .foam file, and you go into the output directory of XDEM, and you open the particles file, and you basically have them as well as, yes. And you get something like that. That means basically this is done with produces ParaView, here the OpenFOAM region, the particles, and you can basically color the particles with whatever, or not whatever, but all the properties that come into ParaView, that is basically surface temperature, interior temperature, masses, species, whatever. And yes, that is basically what you then do in OpenFOAM in ParaView, and it gives you, and you can as well then obviously what I wanted to show you, do an animation where you see then basically, because usually all these things are very transient, where you can then basically show them, okay, this is the things that are happening. Yes, that is that, and that brings me already to the summary. It's 7:05, so I'm well in time because I know I'm standing between you and the pint this evening in the pub. So I don't want to stress your patience more than necessary.
The first presenter has been on time this entire day, I think.
Yeah, because perhaps I want as well a pint. It's the best driving force. Okay, yeah, let's get to the summary. Yes, it's essentially for this discrete continuous coupling between OpenFOAM and the particles, we have a transfer of heat or exchange of heat, mass, and momentum. And these transfer properties are introduced into the relevant conservation equations by source terms on the right-hand side, either by programming it straight away into the relevant equation or through the FV options. And as I say already, the framework will be available soon under xdm.de. I'm still working on it to for you to basically have there this example that I showed you, and then a more elaborated example that includes as well additional reactions for biomass, pyrolysis, gasification, and so on. So you can download all that. You basically have there as well, as I said, all the things. I hope that it's going to be done with copy and paste commands to get it installed, compiled, and running. And as I say, I didn't manage to do that for the foam workshop. So I thought before I'm going to do something hastily and it's not going to work in the end, I'm wait until you have as well finished your summer break and are full of energy and enthusiasm to start this thing. And yes, here, of course, it is not going to work either. An animation for the six-way coupling, as we call it, we have here particles coming in. These particles are lighter than the fluid. These are heavier than the fluid. Here we're having a flap, and this flap experiences force due to the flow and due to the particles impacting here. I give it a try, but I'm not very confident. No, but you find these things as well on xdm.de. So basically, you see this flap here swinging back and forth, of course, then interacting with the particles, the fluid, and so on. We have a nice animation. It's more or less of academic use, but a nice animation, and shows basically the six-way coupling: particles to the fluid, fluid to the flap, and the particles to the flap. Yes, and of course, all these things wouldn't be possible without, yes, truly an excellent team that is developing this XDEM, what I want to say, XDEM software here, just a snapshot from our last what I wanted to say, workshop that we usually have once a year outside the university to see something different. Yes, and of course, thanks go to the Luxembourg National Research Fund, EU project PowderRec and Interact, and of course the HPC Center at the University of Luxembourg. And that means thank you very much for your attention at this late time of the afternoon. And yes, please feel free to contact me. And as I say, if you want me, send an email to me. I put you on the mailing list when the thing is available on the homepage there. So you will get a straight away notification so that you can download the things. Yes, that basically, I think, yes. Thank you very much, gentlemen. If you have any questions, then please answer. No, sorry, please. Please ask now. Yes, please.
Yeah, I've got a question. So how small would you have to make the particles to behave themselves as continuous as in the CFD part?
How to make a particle continuous? I don't understand.
If I think about you basically, if you go down to molecular levels,
yeah,
you're talking spheres interacting with each other. So how small would you have to make particles to behave in a continuous manner?
Yes, essentially, if you want to, yes, I mean, essentially, if you want to go to the atomic level or molecular level, you have to get them to the size of molecules, and then, for example, what I wanted to say, apply a kind of Leonard-Jones potential to model the interaction between them.
Doing a simulation.
Yes, yes, this level kind. But I'm not sure that DEM would be the appropriate tool for doing these things, looking to molecules. Would rather say that Boltzmann is a bit more suited to these things. But I don't have much experience there, I must say. Yes, there was some. Yes, please. Yes, you can download the thing and. Sorry. No, it's not. Main public XDEM is not open source simply because I don't have the resources to maintain an open source repository with all the necessary gadgets to get that done. So you get basically the libs that you then call. You basically in OpenFOAM you have call statements to these libs, and that's it. Oh, okay. Yes, and if you want, yes, depending on what you want to do, just contact me and we find a solution. More questions? I thought there was another one. Yes, please.
For the implementation, are you running in parallel as well?
Yes, good. Yes, thank you very much for the question. I wanted to mention that during my talk, but I forgot. No, thank you very much. No, the thing is basically, of course, all this OpenFOAM is parallel and parallel XDEM is in parallel, but the tricky bit comes when you linking the two together. Because if you have two parallelized codes and you link them, you usually end up with a kind of sequential code, because each code does its partitioning without respecting any kind of constraints from the other side. And therefore, we have developed an new, what we call collocated partitioning algorithm that we apply. Because the thing is basically, let me go back to give you. Yeah, here we are. So basically, let's put it like that, simply speaking. OpenFOAM is, of course, this doesn't make sense if but OpenFOAM does the partitioning here just between these two particle layers. That's here, this is node 1 and this is node 2. So in XDEM, for example, does no partitioning and puts the particles here, the top layer onto node 1 and these onto node 2. That means you have to communicate everything. Or usually what you have to do, you have to communicate everything between all the nodes. And that means if you look into literature with CDFOAM or whatever else, you're going to die the communication death. And so what we have done, our collocated partitioning algorithms makes sure that the CFD domain and the particles inside the CFD domain are on one node. And then you save an immense amount of communication. And that makes the whole thing then very efficient if you run these things on HPC platforms. Yes, please.
Sorry.
Sorry. Yeah.
So my follow-up question would be, let's say you have two partitions.
Yeah.
You put all the part code in the one partition. How are you actually dealing with dynamic load balancing issue?
Yeah. There is not much to do about balancing. It's the partitioning. If you have the party in such a way, you should partition in this way. You should. I mean, these things are. Yes, I mean, what comes together? You need to be a CFD specialist. You need to be a specialist in XDEM. You need to be HPC specialist, and you need to be some other specialist as well. So this is always what I'm thinking, or I was telling my students, before you do anything, or what should you usually, in any case, be the case, before you do anything, think about it, and not the other way around. So it's not always, I mean, first look at the thing, and for the partitioning, for whatever. That helps you quite a lot in saving CPU time. Yes.
Yes, you mentioned that exactly keeping the subject. I'm sorry, but when dividing the different domains, you are going to keep the particles in the same domain that the fluid is going to be.
Yeah.
But if the particles moves inside the domain,
then we do dynamic repartitioning.
Okay.
Of course, that's yes. I mean, in a static case, that's okay. Then the partition from the very beginning. But if parties, of course, what they usually do move, then after some time, when you have reached a certain imbalance, then you need to do repartitioning. Yes. Yes.
Just a general question about the shape of the particles. Are you able to handle cylindrical particles?
Yeah. Yes. Yeah. I mean, these spheres are rather simple, but we can as well do spherical or a large range of different shape. Spherical, cylindrical particles and things like that. So, of course, not all the particles shapes are covered, but a lot of them. Yes, please. Sorry.
So in the Cftdm, even for the fluid phase, we have a base cost grid, right? So which means we couldn't resolve the heat transfer between the fluid phase and the wall.
Yes, of course, we don't have an. Yes, sorry, carry on.
So do you consider the heat transfer through the wall, or currently you only use the wall boundary condition?
Yes, so basically, I mean, of course, we cannot do an. Let's first talk about the particle wall. We cannot do a resolution of the boundary layer around the particle. Maybe I'm doing that with the immersed boundary method, basically to find the heat transfer conditions resolved, and then basically derive from there the integral methods that we know as well from heat mass transfer by Nusselt number or Hrvoje number. And it is essentially what we apply. We take we have a selection of heat transfer law and mass transfer law that are all based on these Nusselt-Hrvoje Reynolds correlations, and that is essentially coming from experimental value, from experimental data that scientists have done long ago to basically derive these correlations with Reynolds number, Reynolds number, that define then the integral heat transfer between the particle and the fluid.
So basically, you consider the heat transfer only from the particle.
Yes, on the particle phase, I mean, from the yes, that's basically the particle phase, between the surface of the particle, and if you have other heat losses, I mean, yeah. So I'm giving you now an answer. I hope this is right. And when we have wall heat losses of the fluid, that is done in OpenFOAM as usual. And if a particle is in contact with a wall, then we have as well a heat transfer between the particle and the given wall temperature, for example. Is that all answered?
Yeah.
Okay. Yes, please.
Can you go to particles larger than cells?
Shouldn't. No, I mean, there are different approaches. I mean, of course, I mean, this particles should be, or the CFD cell size should be the size of the particles in order to apply this thing, because otherwise if the particle is bigger than the CFD cell, you getting then a porosity or void fraction is negative, and this should be the case. But at the moment, or not at the moment, we are working on a coupling that makes the CFD size independent of the particle size. What essentially is behind it is you have what was a dual grid approach. So you have basically a coarse grid in OpenFOAM that does the transfer, and then you map these transfer properties onto the fine grid, and then you run there your CFD simulation. So that we have done already as well, but we have to still work a bit on it to make it a bit safer. So then basically then you are completely independent. We have done that for, because we had a simulation where we had to do high turbulent fluctuation. So we had to resolve the CFD with large eddy simulation, and of course then the particles are not that small. But that means basically is the solution is there. It's yes, going to be there. It's going to be available, I think, coming year. Yes, please.
On the software side, does this mean that in the current approach, OpenFOAM is calling XDEM as a library?
Yeah.
And second, is OpenFOAM then controlling some kind of implicit coupling? And is this the same approach that we're using in the case in the output that you showed?
Yes, I mean the first question. Yes, OpenFOAM is calling. I mean, as I said, I couldn't show it here. This the driver, the directing foam driver. There you insert the statements that calls the XDEM functionality from with libs. And the second question, what was that now? The
if you essentially apply some implicit coupling.
Okay, so at the moment the coupling is explicit, but the implicit explicit coupling is on the way. So they basically have on the XDEM side is already there. On the OpenFOAM side, of course, you can as well in the what I wanted to say, and both in the equations and with the FV options, you can define explicit implicit coupling, but we need to transfer an additional field that contains the implicit term for the implicit coupling.
And then in the case we have the output, we have a third participant, right, for the structure.
Yes, okay, there's, yes, for if we do then what I wanted to say, structure interaction with the particles, then it's the same like with the fluid. If a particle is hitting a wall, it generates a force. And then, of course, this force is again affecting the particle motion, but is as well, but appears then in the FEM code on the right-hand side as a boundary condition. And then, of course, the same philosophy like with OpenFOAM equations. You have then in the what I wanted to say in the FEM equation, the right hand, where you define the boundary conditions for the structure. You have an additional force that is basically a particle force, and then the force is then responsible for the deformation and the stress distribution.
I understand the mathematics, but is then this implemented in the same framework that we have now with OpenFOAM calling XDEM?
Yes, it's the same framework. I mean, it's the same the framework that I was talking about for the implicit explicit communication or coupling that's coming next year. The implicit explicit is coming earlier. The other one with the FEM, yeah, it depends on yes, simple cases will be there as well available. And as I say, be using I'm not writing any FEM code nor any CFD code. Be using Calculix, but you can use any other kind of code like Elm or whatever else, and for your FEM calculation. More questions, please? If that's not the case, then I guess we can head for the pint. Okay, thank you very much again.